Okay, so we're reviewing Fourier series. If you'll recall, a Fourier series allows us to write a periodic signal, x of t, as a sum of complex sinusoids with complex weights ak. These are our Fourier series coefficients. We've been writing this as e to the j k omega naught t, where omega naught is our fundamental frequency. And last time we looked at a case where you didn't really have to do anything terribly complicated to find the Fourier series coefficients. We could just write a cosine or sines in our expression in terms of Euler's formula, basically read those AKs right off. But sometimes you wind up with more complicated signals, and you need a way to be able to find what these AKs are. So for that, let's review the Fourier series analysis integral. There's a 1 over the period that's included in that integral. And there's also an integration over any period. So this integration, it could be between 0 and t naught, or it could be between minus t naught over 2 and t naught over 2, or you could have minus t naught to 0, or something like minus t naught over 4 to 3 t naught over 4. Whatever period. In theory, any period will work. Now, depending on how your x of t is defined, how it's given to you, some form of these integrals may be more or less convenient than others. So which one of these you would try to write down and try to work with may depend on what it is that you're actually trying to do. So let's continue this expression here. So what we'll do is say, okay, let me try my eraser. Ooh, I can erase with this tablet. That's kind of cool. I flipped the pen over. Anyway, so we're going to integrate our function over one of these periods. We're going to integrate it against e to the minus j omega naught kt. And the minus sign here is important. If you look into the sort of text that we're writing, or pretty much any textbook on the subject, you'll see why there's a minus sign there. And this is basically the magic you need in order to take this periodic signal and split it up into its individual sinusoidal components. Remember, when you see e to the j something t, you're so used to thinking about e to the something t algebraically. You're used to thinking of e to the 5t or e to the minus 5t for an expanding or decaying exponential. But when you see this j, really you should be thinking cosine sine, think sinusoid. The e is sort of notation is a convenient way to let us avoid a bunch of trig identities, but these are sinusoids, so think about wavy things whenever you see that. Let's put a dt here to close out the integral. And let's look at a particular example. So suppose we had a signal that was a square wave. Square wave is not the best term for it. It's a pulse wave, periodic pulse wave. And when it has a 50% duty cycle, people will typically call this a square wave. Square is not really great because it somehow implies that your time scale here, so this keeps going each direction, dot, 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 dot. Their time scale is somehow on the same sort of unit scale as your vertical axis, which doesn't really make sense, but people call it a square wave anyway. So if we look at a period, so let's say that these waves are periodic with t naught, these little individual, I don't want to call them wavelets, little bitty wave kernels. I don't even want to say that. You know, bits of this wave, the repeaty bit of the wave. Let's say they have height 1, and let's say there are 50% duty cycles. So if this guy goes up to t naught over 2 from minus t naught over 2, what do we have in here? Or this is going from t naught over 4, the part of it that's a 1, and say t naught over 4. So this is a very natural part of this function to grab as our periodic part that we're going to use for doing the integral. So let me make some space at top, and we'll start actually I deleted the whole thing. Did I mean to do that? I didn't, but that's not sure how I did that. Anyway, I meant to just delete the top, but let's go for it anyway. So you can rewind if you need to. So what I'm going to do is I'm going to, well, let's be a little silly here. So I'm going to say, let's pick out this middle period here, and what I'm integrating, well, x of t will let me plug in x of t. So I'll have a function going from t naught over 4 to t naught over 4. And I've got e to the minus j k. At this point, let me go ahead and write this. Omega naught is 2 pi over t naught. You'll see why that becomes really convenient in a second. Now, don't tell any actual math people that I did this. But here's your function. I just sort of drew a graph in there. It's probably not what you want to do on a test for your math professors, or even for that matter, most of your engineering professors. But here's a little graph defining that wave fairly unambiguously. And notice it's kind of unique. We could sit there and write this in terms of a unit step function minus unit step function, or even a unit step function times another unit step function. But all of those are really kind of obscuring what the function actually is. And it just kind of is more clear if you look at it and say, okay, there's the function right there. Anyway, usually I probably would not even have written this step. Notice that it's 0 outside of there, so let me take that into account. If I want to be pedantic, I could put a 1 here, times e to the minus j k 2 pi over t naught dt. And what I'm going to do is I'm just going to chop the limit. So this is going to go from minus t naught over 4 to t naught over 4. Again, if you wanted to be super pedantic, you could say, well, there's the lower part of the wave here, going from minus t naught over 2 to minus t naught over 4. Basically, this little section in here. But it's 0 times e to the blah, 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 which, of course, is 0. Same thing for the upper bit here. And so we just generally won't want to write those down. But remember that they're kind of there hanging in the background. But there's not really a whole lot of point in writing those things in there. So I've got this nice little integral. I try to remember how to do my freshman calculus. I'll write this as, let's see. I'm integrating, oh, there's a t. Sorry, I do this all the time. There should be a t here. There should be a t here. And what I've got in the denominator, I'll write this as minus jk 2 pi over t naught. And then the exponent here, they've got e to the j k 2 pi over t naught t. So there's my indefinite integral. If I take the derivative of this business in front of the t comes down and cancels with all this junk I wrote in the denominator. And I need to evaluate it at its limit. So I'm going to write that as t equals 0 to t equal, no, sorry, not t equals 0. It's t equal, I need my eraser again. What are the limits of my integral? So t is equal to minus t naught over 4 to t naught over 4. And I need to plug these things in. So let me make some space up here. So we'll just sort of continue the derivation up here. I can't really call it derivation. It's just boring algebra, right? So let's clear out this, and we'll clear out some space here. I just bought this Wacom, whatever tablet is today. Whack-a-mole tablet, whatever it is. Anyway, however you pronounced it. So I'm still getting used to it. Anyway, so this, no, we're doing AK, right? These are the AKs that we're computing here. Let's go ahead and put those limits in. So I've got minus 1 over jk 2 pi over t naught. And that's the thing that's sitting out in front. And what do I have here? I've got the limits. I've got e to the upper limit here is the, so there's a minus sign from there, is e to the minus jk 2 pi over t naught. And here let me plug in that upper limit. So plugging in that upper limit for t, I've got t naught over 4. And then, well, what's the next thing? Well, it's the same thing, except here, when I plug in that limit, the 2 pi over t naught, this is minus t naught over 4 that I'm plugging in here. This is just boring calculus. It's boring calculus where it's very easy to lose track of the details and lose a sign or some symbol So you do have to be careful. But gloriously, these t-naughts cancel, these t-naughts cancel. And if I then, let me clear out some more space down here to draw the next line. So I'll say, okay, let's delete all that. Let's see if we can simplify this a bit. Well, let me pull the minus sign through. Oh, there's another error I made here. This should be minus. It's the lower limit of the integral. So let me pull this minus sign through. Cancels with this minus here. So I'll write this in front. I'll write this as j k 2 pi over t naught. This is what's sitting out in front. And, oh, there's this other thing I forgot. So what I'm computing here is not actually AK. What I'm computing here is T naught times AK. There's a 1 over T naught that you want to include in your derivation of the AK. So let me go back and see if I can retrofit that without making this too disastrous. So we'll say, oh, 1 over T naught. So that causes these T naughts to cancel, and the thing that you always want to have happen happens, which is you really want this AK to not be a function of T naught. If you wind up with an AK where there's a function of a T naught, it's very likely that something funky has happened someplace along the line. So let me clean this up a little bit. So put the 1 over 2 pi here. Okay, so what do I have here? I've got e to the minuses here cancel, gives me a plus jk. I've got pi over 2, since I have a 2 up here and a 4 down here. So I've got pi over 2, and I've got minus e to the minus jk pi over 2. And now something very interesting happens. If you look at this guy, we see I have e to the stuff, e to the minus stuff. So I have these complex conjugate pairs. The one with the minus has a minus sign in front of that there. And I have a 2j sitting out in front. So if you are a Georgia Tech undergraduate, this should immediately jump out at you as the Euler's form representation for sine. Some people refer to this as an inverse Euler's formula. I think that's being a little overly pedantic. But anyway, I can rewrite this using a sign. So I'll write this as 1 over pi k. And then the rest of this here, this j, this 2, all of this stuff over here, all of this conspires to give me a sine k pi over 2. Now, on its own, this is really kind of about as simple as you can get it. There are some caveats. The k equals 0 case is special. Well, I'll come back to that one a little bit later. The thing to remember when looking at this expression is that this k is an integer. So if you look at what sine k pi over 2 does, and a lot of Fourier series expressions, when you, I should say Fourier series analysis integrals, when you crank through it, they'll give you something that looks like this, some sort of sine or cosine with some integers, and there's some pi's and some 2's and whatever. In general, this is something pretty complicated, but you'll see in this case, the sine k pi over 2, it's really just a super fancy way of writing a mapping that's a function from k's to either 0s or 1s or minus 1s. So there's not really a cleaner way of writing that per se, but let's try this out for a few values just to get a feel for what this kind of expression really does, what it really looks like. So let me clear out all that, and let me clear out all this. When I get a little more practice with the tablet, I'll make this a little smoother. Anyway, so let's explore what this guy is. So this guy, remember, this guy is our Fourier series coefficients, AK. Again, k equals 0 is a little strange. I'll come back to k equals 0 later. But let's make a little table. Let's see what is k for, say, k equals 0. Let's see what sine k k pi over 2 is for different values of k. So for 0, this is just 0. And that's where this gets weird. You get 0 over 0. We'll have to treat that a little more carefully. We'll come back to that. What about 1? So sine pi over 2 is just 1. What about 2? Well, sine of pi, we might go ahead and remind ourselves what sine looks like between from 0 to pi to 2 pi. That's going to be just 0. We're back here. What about 3? Well, that's going to be minus 1. That's 3 pi over 2. That's going to put us down here. So that's minus 1. 4 is going to give us 0 and so on. But what if we continued this kind of graph and looked at minus 1? Well, that's going down this direction. So for minus 1, our graph would be minus 1. But for minus 2, it would be 0. But for minus 3, it would be 1. Right? Because that's kind of coming back up here and hitting that part. So this function is really just alternating 0, 1, 0, minus 1, 0, 1, 0, minus 1. It has this very particular pattern. So that gives us a hint on how we might plot that and how it's operating. Before I try to actually make a plot like that, let's go ahead and talk about this k equals 0 case. So let me zero out this guy here. Let me zero this guy out here. And let's talk about k equals 0. So for k equals 0, couple ways to handle it. One way is to use L'Hopital's rule on this. So let's say we said a 0 was, let's treat this as taking the limit of this as k goes to 0. So I'll write limit as, no, that's, I was starting to skip a step in a way that wasn't quite sensible. Let's say we're taking the limit of this as k goes to 0. So I have this form sine k pi over 2 in the numerator. I've got pi k and the, oh, sorry, that's just awful looking there. And in case you're wondering if you're watching this on YouTube or something, you haven't actually had a class with me, I must confess my handwriting on the board it's pretty much this bad. Anyway, so blah, 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 blah. Okay, I want to use L'Hopital's form on this. So what I'll do is I'll take the limit of the numerator and the denominator separately, but for L'Hopital's to work, I need to take the derivative of each of this numerator and denominator separately. So when I take the derivative of the numerator, I'll get a cosine, and by the chain rule, this is a 2, not a t, by the chain rule, taking the derivative with respect to k, I'll get a pi over 2. That sits out in front. What about down here? Well, the derivative with this respect to k is just pi. And those pi's cancel. The k down here doesn't even matter. When I take this cosine, limit as k goes to 0 is just 1. So this is equal to 1/2. Now, this makes sense if we also compute a0 another way, which is say, oh, let's go all the way back and look at the original Fourier series formula. Sorry, the Fourier analysis integral formula. Looked like this. It looked like ak equal 1 over t0 integral over any period xt e to the minus j k omega naught t dt. Now, if you look at one particular special case, so let's look at the special case of a0. So let's plug in k equals 0. Before I do anything else, if I just plug in 0 here, then this simplifies drastically. If I plug in 0 for k here, e to the 0 is 1. So I wind up just taking the average of the signal over a period. People will typically call this the DC value for direct current, because at least as we in electrical engineering think about the field, that started thinking about currents, people will still quite often use that term DC direct current. just for a k equals 0 Fourier series coefficient, even if there's no current, even if there's no concept of electricity at all involved in whatever problem you're looking at, people still tend to often call that the DC value. It's basically the constant. It's an offset on your waveform. It's the center value of your waveform. And that makes sense if you look at the actual function itself. So let's use, so this thing down here, this is a general trick that works for whatever waveform you're looking at. If on a test, if you have this horrendous xt that you have to deal with, but you notice the professor is only asking for a naught, what the professor is trying to test to see is if if you try to compute the AK for a general K and it turns into this massive nightmare of equations, the idea is if all the professor is asking for is a naught, don't do that. Don't compute it for general AK and then substitute K equals 0. Use this kind of trick to compute it pretty easily. And it makes sense if you look at the square wave we've been whacking on for a while now. Let me use my sort of funky notation. It's 1 over T naught, some integral over T naught. It's the integral of this, right? Between T naught over 4 and T naught over 4 dt. So this is just a rectangle. It's got a length of T naught over 2. It's height 1. So it has an area of T naught over 2. Well, and then it's the average of that signal. So I divide by that T naught. And so I get 1/2. So these match up. What I get with L'Hopital's is the same as what I got using this trick. A couple of caveats before we keep going. One is that when we talk about the area, remember that an integral is a signed area. I just computed the area of the rectangle and said that's the answer, divided by T naught. And I was able to do that because it's just positive. If part of this went negative, then whatever area that is needs to be subtracted off the positive. Just remember that. The other little caveat is that for L'Hopital's theorem to work, there are a variety of technical conditions that need to hold. And if you go to a calculus book, will provide you with all sorts of examples of places where if you blindly apply L'Hopital's rule, you'll take these derivatives, let these limits go to 0 or whatever, and you'll get some answer. You'll get some number. But that number doesn't actually correspond to the original limit in any sensible way. If you are my student in ECE3084 at Georgia Tech, I'll promise you that in this course, within ECE3084, at least as you take this course from me, Professor Aaron Lanterman, the uses of L'Hopital's rule that I will use in class or ask you to do on a homework will work. We will be limiting our experience to a certain set of cases where L'Hopital's will work for the things we need it to work for. If you go over to the math department, they may be a little sneakier about that. So you'll want to go in and dig in and check those conditions. So anyway, let's stop here. What I'll do in the next part of this video series is we'll actually plot the Fourier series coefficients for the square wave and wax philosophical about them for a bit. So I'll see you soon.